Good morning everyone. So this is my next lecture in continuation with the last lecture, that is lecture number 13 based on Zener diode. So this lecture basically deals with the Schottky diode. We have covered something a little bit about Schottky diode, the construction of this Schottky diode, the basic features of this Schottky diode, and in this lecture we are going to see the characteristics of Schottky diode, the advantages and disadvantages of Schottky diode as compared to Zener and the normal PN junction diode. Then we will move on to PN junctions and BJTs, and BJTs, in that BJTs we will see the structure point of view of the BJT like NPN or the PNP type of BJT and their characteristics and so on. So moving towards Schottky barrier diode, we have discussed earlier also. The Schottky diode is basically named after a German physicist, that is basically Walter H. Schottky, also known as hot carrier diode. So basically Schottky diode is also known as hot carrier diode, and it's a semiconductor diode with a low forward voltage drop and a very fast switching action. So here the switching action is very fast as compared to the Zener and the PN junction diode. The voltage drop is here 0.6 to 1.7 volts. A normal silicon diode has a voltage drop between 0.6 to 1.7, while the Schottky diode has a voltage drop between 0.15 to 0.45 volts. So this is the major difference between a normal diode and a Schottky diode. The voltage drop across the junction between P and N type, there is a voltage drop of around 0.6 to 1.7 for the normal diode, and here 0.15 to 0.45. So these are major points, that is switching speed of this Schottky diode is much higher. So switching speed is much higher as compared to the normal diode, and the voltage drop is also very less as compared to the normal diode because it is 0.15 to 0.45. So it will give you more current as compared to the Zener or the normal PN junction diode. So this is voltage drop. So voltage drop is very less, that is around 0.15 to 0.45 volts. So these are two major points here for the Schottky barrier diode. If you see about the structure of the diode, it is similar to PN junction or the Zener diode. This is the positive terminal, this is the negative terminal, this is the anode and the cathode, and it's the same as Zener type of structure here. So next, construction of Schottky diode. Other diode types like Schottky diode, which is also known as hot carrier diode, which I have told you in the last lecture and this also. So significant characteristic, it's fast switching speed, which is a major advantage of using Schottky diode. This is useful for high frequencies operations and digital applications, like we want to have a switch or a digital various digital application nowadays, microwave devices and all, these are made up of Schottky diode. So it is not a typical diode in that it does not have a PN junction in it. So instead it consists of a lightly doped N material and heavily doped conduction band electrons, metal bonded together. So response here is very quick, high speed digital communication. So as we know now, the era is changed from analog to digital communication nowadays, and we require more and more digital input from the transmitter side. So we have to convert analog signal into digital signal, and later on we will transmit that digital particular transmitter transmit that digital signal into the receiver through the channel. So that's why Schottky diode plays a very important role whenever we require a high speed digital application. So wherever we require a high speed digital application or digital communication, we can use our Schottky diode. So this is a symbol, same symbol, that is this one is the positive part and this one is the negative part. We have represented also on the basis of the lightly doped and heavily doped conduction band electrons, that is the cathode side and the anode side, the N region, which is the negative region, and the P region, which is the positive region here. So we have a metal silicon junction in between the P and N junction. This is P and this is N. So in between the P and N junction, there is a metal silicon junction, which is a metal region, and the P region is heavily doped conduction band electrons and the N region is lightly doped. We just apply the biasing here and the current will flow as similar as in the case of the Zener and the normal PN junction diode. So for forward biasing, we have to apply a positive voltage supply to P type and negative voltage supply to N type, so that the electrons will move towards the junction and the holes will also move towards the junction and they will cross the junction and the depletion layer becomes narrower. In the same way, we can provide the negative biasing here in the case of the Schottky diode, and in that case N type of material is connected with the positive potential and P type of material is connected with the negative potential, and in that case obviously the holes will get attracted towards the terminal, and similarly the electrons will attracted towards the positive terminal, and they will not cross the junction, and that's why the depletion width will become much higher. So here the depletion width is not same as the PN junction or the Zener diode. It's a metal silicon junction, we can say. So this region is basically metal region, and the N region is the silicon region. So silicon region is lightly doped, the metal region is heavily doped here. So now coming to operation of Schottky diode. As we apply the voltage, then electrons will move from semiconductor to the metal region, and current will move from metal to semiconductor region, so that it produce high current in the given construction. So as I have already discussed about that, this is the metal region here, this is the N type region here. So what we are doing, metal region is basically P type. So what we are doing here, we will apply positive voltage to P type metal region and negative voltage to N type. And obviously when you provide negative here and positive here, so the holes here which are in majority in the metal region and the electrons which are majority in the N type of region, the electrons will get repelled from this negative charge and they will cross the junction and make a negative ions towards the P junction. So this negative ions which are created by the N type of electrons moving towards the P junction. Similarly, from the holes will get moved towards the N junction and they will create a positive ion in the N type of semiconductor material. So this will create positive ions. So there are two types of ions created in the depletion region as similar to the PN junction, that is the negative ions and the positive ions. So now the current will flow, electric current will flow from N type to P type, from negative to positive direction. And this particular region is called your depletion region, which is already we have discussed in PN junction also. Only the difference is what? The P type here material, semiconductor material is not present here. Here the P type is metal. So the combination of metal and N type will create a Schottky diode. So the junction is metal and N type of junction. So the junction here in the case of the Schottky is metal semiconductor, not semiconductor. This is the case for Schottky. While in the PN junction or in the Zener diode, we have semiconductor or semiconductor junction. Other things are similar to the PN junction. The Schottky diode, whatever the depletion region is created, whatever the ions, negative ions and positive ions are created, are similar to the PN junction or the Zener diode. So here the current is very high as the contact is metal and N type. The switching speed is very high, fast switching speed, and these are used in various digital applications. So these are major points for the Schottky diode. So coming to the characteristic of the Schottky diode, since Schottky diode has a fast switching action, we already discussed, due to its spatial construction, therefore as a result, the characteristic of Schottky diode is before the ordinary diode as seen in the diagram. So you can see, just see, we have plotted both the PN junction and the Schottky diode, V and I characteristic. So here the PN junction is, you have this point is basically built-in potential, or we can say knee voltage, which is for silicon it is 0.7 and for germanium volts, and for germanium it is 0.3 volts. So here the PN junction, when you increase the forward biasing, for some stages, for some time, the current will not increase. So up to this point the current will not increase, but after this point, when you increase the voltage to crossing the knee voltage of 0.7 or 0.3, whatever semiconductor device you are using, so in that case the current start drastically increasing. So you can compare the Schottky diode with the PN junction diode. In the Schottky diode, the knee voltage is lesser as compared to the PN junction diode. So we can say in the case of Schottky diode, we have this conclusion, that is Vk for Schottky is lesser as Vk for normal PN junction diode. So which will give you a better result, because if the knee voltage is less, then for a small operating point of the voltage, or whenever you give the small voltage, the current will start rising. So the Schottky diode has a current increasing type of exponentially increasing function. Both the things have exponentially increasing function, but the Schottky diode has lesser knee voltage as compared to the PN junction. On the other hand, we can see on the reverse bias condition also, the Schottky diode has a Zener breakdown, or you can say avalanche breakdown is earlier as compared to the PN junction diode. In the PN junction diode, we require much higher voltage to have a abruptly change in the current, but in the Schottky diode, we have lesser voltage as compared to the PN junction to get our current abruptly increasing in the reverse direction. So we can have a difference between both Schottky and the PN junction diode. Both are having different applications. Wherever we required a digital applications, wherever we require fast switching, we can use Schottky diode. Wherever we require not a normal speed switching or BJT functions, then there we can use our PN junction diodes. So now what are the applications of the Schottky diode? So Schottky diodes are used for the voltage clamping applications basically, and it is used to prevention of transistor saturation, which is due to the high current density in the Schottky diode. So here the current density is very high. It also be a low forward voltage drop in Schottky diode. It is wasted in less heat, making them an efficient choice for application that are sensitive and and require very high efficiency. Schottky diodes are also used as rectifiers in power supplies. So major applications of Schottky diode as a digital application, as a power supplies, as a low voltage drop industrial applications, and it is used for clamping applications also. So these are some major points. First point is, the main points are clamping applications. And the second one is as a power supplies. Both these applications are very much important. And last you can say as a digital applications, wherever required fast switching, wherever required fast speed is fast required. So these are all are the applications of the Schottky diode, where we can use Schottky diode in a better way. So next, coming to the next part of this PPT, that is BJT, that is bipolar junction transistor. As we can have the name, that is bipolar, so it has two polarity, that is P and N type. So a bipolar transistor essentially consists of a pair of PN junction diodes that are joined back to back. So what we have done here, two PN junction diodes are joined back to back, and they will give you this type of structure, that is P and N and P and N. So obviously it will be NPN type of structure, or in the similar way we have PN or PN, it will give you PNP type of structure. So these type of diodes will be created with the help of, or PN junction transistor will be created with the help of the two PN junction diodes that can be joined back to back. These are two kinds, that is NPN and PNP varieties. So the three layers of the sandwich are conventionally called as the collector, base and emitter. So we have three points here, that is emitter, base, collector. So this point is emitter, this point is base, this point is collector. So collector is basically for collecting the current, emitter is base and emitter. In between the base and emitter, the current will start initiating, or you can say that that will give you the input current. Similarly here, this is base, this is collector, this is emitter. So for PNP, for P and P, because it is P, sorry, this is P, this is N, this is P. So the current will flow from positive to negative direction. Similarly here, this is N, this is P, this is N. So current will flow from P to N side. So obviously the current will flow from P to N side. That's why we have make sure that the arrow of this particular symbol will be clear to you. So the arrow from P to N side. Similarly here from P to N side. So for P and P, it is having the inside arrow, and for NPN it is having the outside arrow. So this will give you the overview of the BJT. What is BJT? So this can be clearly understood that BJT can be formed with the help of the two back-to-back PN junction diodes. So these are some generalized diagrams of the BJT. So here we have a BJT which you can use in the lab. So we have emitter base collector. I have shown you that is for PNP type. So this is P, this is N, this is P. The current will flow from P to N side. Similarly, this is N, this is P, this is N. The current will flow from P to N side. So in this diagram, in the below diagram, we have shown the voltage source, the resistance value, both one PN junction transistor, that is emitter base collector, is connected, which is obviously NPN type. This is N, this is P, this is N, because from P to N the arrow is given, so obviously it's a kind of a NPN transistor. So we have a voltage source between base and emitter, which is VBE, positive side is connected, because this is positive, this is negative. Okay, so the voltage base and emitter, in between base and emitter it is VBE, in between collector and emitter it is VCE. So we have applied two voltages here, VBE and VCE, and we have grounded the base point, that is to be grounded. So the current will flow from this resistance, which is the base current IB, and the current in the emitter circuit, that is IE, which is ground towards the ground, and the current which is collected through the output resistance, that is at Vout, that is IC. So we have these three currents, that is IE, which is because we have connected emitter to the ground. Then VBE is the voltage source, and VCE is the voltage source for the base emitter junction, and this is for collector emitter, and the input voltage is Vn and the output voltage is Vout. So we have drawn the characteristic curve between VCB and IC, because we have connected VCB is the output and input, and the current, that is IC, flowing through the output circuit. So VCB and IC, and here I is, because I is common emitter configuration is this, so I is grounded, so we have taken I as a constant. So at I is equivalent to 0 ampere, at I is equivalent to 10 ampere, then 20, then 30, then 40, then 50, we can see that there will be a, whenever you increase the voltage, there will be an increase in the collector current. So whenever you increase VCB voltage across collector and the base, then there will be an increase in the collector current. So this is the generalized diagram for the BJT, that is emitter base collector 3-pin BJT, and these are both the same thing, that is PNP type, that is emitter base collector. Similarly NPN type, that is base emitter and collector, and we can show from by a circular structure also, like emitter base and collector, and here also this is NPN. The current will flow from P to N side. So if you see here, that is the emitter is connected with a one BJT or one PN junction diode, and the base is connected with another PN junction diode. This will form as, this is P, this is N, this is again N, this is again P. So it will give you PNP type of BJT structure. So this is PNP. Similarly, this is NPN, because this is N, this is P, this is P, this is N. So this is NPN, or the current will flow from, if you see, the current will flow, so here the current will flow, because this is N, this is P, and this is N, the current will flow from here to here. So we see, we can draw these diagrams for generalizing the BJT structure. So generalized diagram next continued, that is BJT symbols for PNP and NPN. So here emitter base collector is shown at the top. You can show on the same pattern here. So we have these two structures. Then we have constructions point of view, that is emitter base junction. You can see here emitter base and collector. This junction is basically emitter base junction. This junction is base collector junction. Similarly, collector base junction is this one, collector base junction. So we have diode analogy, which we already seen here, and this is a symbol for the generalized diagram for the BJT. So with the help of BJT, we can have different type of applications of BJT. Is BJT as an amplifier you can see, or you can construct a bipolar junction transistor instrumentation amplifier. In the instrumentation amplifier also we can use multiple BJT bipolar junction transistor, and we can create our instrumentation amplifier. These are some generalized diagram. So this is a correct BJT characteristic, which is for common emitter, and for the common emitter it is VCE and IC, which already we have seen. So this is for common base, because here we have taken the base current is common, that is for IB is equivalent to 0, then IB is equivalent to IB1, and then IB is equivalent to IB2 is greater than IB1. So as we increase the base current, we have an increase in the collector emitter voltage. We have also increase of the collector current. So this particular region is called cutoff region, because here the current is, there is no current flow as you increase the voltage, and above this cutoff region is the active region, because this is called the linear curve. So this is the linear region. So as you increase, same, the exponentially increasing function. So this is the linear region, and below is the cutoff region. Linear region is the same thing, that is the active region. In the second graph we have input characteristic VBE. This is VBE and this is IB. So as you increase the base and emitter voltage, you have a drastic increase in the change in the current. Similarly, we have output characteristic, that is VCB and IC. This is VCB and IC, and we have the base current common here, IB1, IB2, IB3 and IB4. So with this graph you can see that there is a cutoff region below the IB is equivalent to 0, and above IB is equivalent to 0 whenever you increase the current, that is from IB1 to IB2 and to IB3, and you increase the voltage between collector and emitter, you have a change in the collector current. So here VCE is increased, IB having some constant value, and IC will get increased for a particular, and there are two regions, one is cutoff region and the other one is the active region, which is called as linear region. So these are some conclusion. This is the linear region where the current will increase as you increase the voltage. So this is the BJT characteristics. So in the next lectures we are going to see how the BJT is important in different industrial applications, like we have discussed that BJT as an instrumentation amplifier, BJT as a variety of different digital applications where we can use Schottky and the BJT in the same way. So if you want to do these experiments in the lab, you can find out the characteristic curves for common emitter and finding out different H parameters of the BJT in common configuration you can do. So in the same way, as we have discussed about PN junction, so we can form the two PN junction, we can create a BJT structure. So by combining two PN junction, like in the form of the NPN or in the form of the PNP, we can create our BJT. So in fact BJT has much higher, much wider application as compared to the Zener and the normal diodes. Normal diodes can be used in multiple applications in appliances also, but BJT can be used as a industrial applications, like as an amplifier, as an instrumentation thing, or something very vast. So in the next lecture we are going to see about something more important about BJT structures, and then we are going to see about FETs, what is the difference between MOSFETs and the BJTs. So in the MOSFETs we have gate source and drain type of thing. Here we have emitter base and collector type of thing. So we have different configuration. The first configuration is common base or the common common base configuration which we have shown in the characteristic curve. Similarly, we have common emitter configuration. Similarly, we have common collector configuration. So thank you so much. We will meet you in the next lecture.